Um, Good evening, everyone, and welcome to our seminar. And it is a great pleasure to introduce our speaker today, Professor Paolo Mancosu, the Willis and Marion Slusser Professor of Philosophy in the Department um, of Philosophy at Berkeley. And Professor will be presenting on the topic three applications of Zermelo's theorem on part whole. So, Professor Mancosu, thank you very much for joining us and agreeing to give us this talk today. We're really and truly honored to have you here. So I think we can start.
Okay, well, thank you very much. I'd like to thank, first of all, Ramazan Ayupov and Arnold Grigorian for this invitation. It's a great pleasure to be in Moscow, even if online and virtually. So this talk is a presentation without too many proofs of the results of three different papers that are published on this theorem by Zermelo, which I will explain in a second. But here's the overview of the talk. We're going to start with presentation of Zermelo's theorem on part O and the three areas of applications, which are neologicism and inconsistent abstraction principles, the axiom of choice in second order logic, and then part whole and regularity in probability theory. So those are the three areas of application. Now, so this is the aim of the talk, to give you a general overview. So as I said, I'll be short on proofs, but if you want to see the details, you can access the articles which are already published. So these are the three articles I'm referring to. The first one published in 2019 with Benjamin Siskind on neologicist foundations, and then in 2023, still with Siskind, but with Stuart Shapiro on choice principles in second order logic, and finally in 2024 in Philosophy of Science, a paper on probability and issues of regularity and cardinality. Now, what is common to all these articles is the exploitation of a theorem by Ernst Zermelo to situations in which the relation of strict subset inclusion, this is what I'm calling part O, is of relevance. So the theorem in its set theoretic version is implicit in Zermelo's famous paper on the equivalence of the axiom of choice and the well-ordering principle. But it was only brought out explicitly in an article by Kanamori in 1997. And it's a wonderful result, partly because of how simple it is to state and the kind of far-reaching consequences that it has. So here it is. Take an arbitrary set X and an arbitrary function from the full power set of X into X. Okay, so no conditions on the function, just any arbitrary function from the power set of X into X. Well, then there are always sets A and B in the power set of X, such that A is strictly included in B, and the function identifies the values of A and B under, of course, that function mapping. So you can prove this theorem by transfinite induction without using the axiom of choice, and I'll show you how to do it in one slide. When I speak of failure of part whole, what I mean is the fact that a function such as the one discussed in this theorem by Zermelo fails to keep track of the strict subset inclusion between some sets A and B, yielding f of A equals f of B, despite the fact that A is strictly included in B. So one way to put Zermelo's result is that any function from the power set X of a set X into the set itself will fail necessarily to keep track of the strict subset inclusion. How do you prove this theorem set theoretically? Well, the idea is to build witnesses for sets A and B so that A is strictly included in B. And you do it by transfinite induction. So just to give you an idea, we have this function that is sending the power set of X into X. Well, look at what the function f does on the empty set. We know it is giving us an element of X. So call this element X0 and put it in a new set B you are constructing. Then now look at what f does when it is applied to the singleton containing X0, right? That's a subset of X, so it's in the power set of X. Well, if this is again X sub 0, we're done, because now we have two sets, A, the empty set, and B, the singleton X0, which are sending exactly to the same value. And so we have the failure of part whole. If not, then f of X0 is some other X1, which is not in the singleton X0, and we put this X1 in B. And so you keep going now. You look at what the value of f on X0, X1 is. Well, it's either X0. If it is either X0 or X1, then you're done. You have your counterexample to the preservation of part whole. And if not, you keep going. But eventually, right, this is the transfinite induction, eventually you run out of elements. And when you do, what happens is that in the end of this process, we will have a well-ordered set B, such that for all proper initial segments Z of B, f of Z is the next element in the well order. But when you're done with the process, you're going to get that f of B must be inside the set B, since otherwise we could continue building B by adding f of B to it. But by construction, f of B got into B by being the f value of some proper initial segment A of B. In other words, f of B equals f of A, with A strictly included in B, and therefore part whole is violated. So this is the standard proof in set theory by transfinite induction. Now, when we apply this stuff to neologicism, and I'm going to tell you what neologicism is, you have to keep in mind that with neologicism, we're working in a second order framework, and I will say more about that. So what is neologicism? Neologicism emerges in the contemporary debate in philosophy of mathematics with Wright's book, Frege's Conceptions of Numbers as Objects from 1983. Wright's project was to show the viability of a philosophy of mathematics that could preserve the key tenets of Frege's approach. Now, prima facie, this would appear to be as an impossible task. After all, Frege's foundational system, as presented in the Foundations of Arithmetic and in final formulation in the Basic Laws of Arithmetic, relied on the use of extensions codified by means of the notorious Basic Law 5 in the latter work, a law that was shown by Russell to lead to contradiction. But if you think about what Basic Law 5 does, it really postulates the existence of a function delta that maps the concepts into the objects of the domain in such a way as to satisfy the following statement. For all concepts x and y, the delta of x equals the delta of y. So think of the delta as the extension of x equals the extension of y, if and only if every object that falls under x falls under y and vice versa. So if and only if the two concepts are co-extensional. Now, if this talk about objects and concepts bothers you, you can think of it extensionally just by taking concepts to be subsets of the domain of individuals. In fact, that's the way we treat model theoretically this kind of Fregean framework. Okay, so it is easy to show that basic law 5 yields an unrestricted comprehension axiom, which in turn yields the existence of Russell's paradoxical set. Frege himself and a few others after him tried to tweak basic law 5, but with no success. And until Wright's book, Frege's foundational project was no longer considered viable. Wright's approach emerged as a combination of a powerful technical result and a host of philosophical argument. The technical result was motivated by the observation that in the foundations of arithmetic, Frege used extensions only in order to prove what is now called Hume's principle, which for Frege was kind of a criterion of adequacy for the value of his approach. And Hume's principle says that for every concepts x and y, the number of the concept x equals the number of the concept y if and only if there is a one-to-one mapping between the objects falling under x and those falling under y. This is in a way a kind of, enthroning of the Cantorian notion of cardinality in Hume's principle. You use one-to-one correspondence to give a criterion of identity for the cardinals associated to the concepts. So it's important to remark that just as in the case of basic law 5, the right-hand side of the biconditional can be expressed in purely logical terms. So in basic law 5, you have on the right side of the biconditional an equivalence relation defined by coextensionality. In Hume's principle, you have another equivalence relation among concepts defined by one-to-one correspondence. So really all these principles, which are called abstraction principles, have the property that they start from an equivalence relation on concepts, and then they abstract from that, that's why they are called abstraction principles, a function that sends the concepts into objects of the domain. And remember that in this setup, the domain is given at the outset, so that you're not enlarging domains or anything of this sort. There is a universal domain on which you start. You have automatically your concepts there as subsets, and then the map takes the concepts and sends them back into the objects. Now, what Wright and later Boulos and Hack showed was that once Hume's principle was established, Frege did not have any further use for extensions and proceeded in the foundations of arithmetic to provide an outline of how to prove from Hume's principles the basic axioms for second-order arithmetic. Now, this technical result was Wright's detailed reconstruction of how to derive within second-order logic the basic axioms of second-order arithmetic from Hume's principles and definitions. So let's call FA for Frege arithmetic the system of second-order logic with Hume's principle, and let's call PA2 the axiomatic theory for second-order arithmetic. So Wright's results then can be summarized as from Frege arithmetic, we can get in second-order logic and definitions, of course, the second-order theory of piano arithmetic. So no need of extensions if you can start taking on board Hume's principle to begin with. Now, this discussion has led to a detailed scrutiny of abstraction principles, of which BL5 and HP are the two most famous instances. Indeed, one of the first objections to assuming or accepting Hume's principle was an argument, which was the first form of the bad company objection. And the argument questioned the legitimacy of using definitions such as Hume's principle, arguing that something fishy must be going on, as shown by the fact that BL5 has exactly the same definitional form, but gives rise to a contradiction. So why should we trust Hume's principle to be any better? Well, this led to the first requirement of a long series to come for separating good from bad abstractions. And that first criterion was consistency. So the idea was, well, the reason why BL5 is bad and Hume's principle is good is that from BL5 you can get a contradiction, but we can actually show that Hume's principle is if is consistent or it's equiconsistent with second order piano arithmetic. And since no one really doubts the consistency of second order piano arithmetic, we have good evidence for the consistency of Hume's principle. Now, if we restrict our attention to operators or functions from monadic concepts to objects, BL5 had been, until the appearance of my work on the subject, the only example of an operator giving rise to inconsistency, thereby making it appear at BL5 as a sort of monster in an otherwise regular universe of abstraction principles free from this pathology. But the use of Zermelo's theorem here is crucial for showing that BL5 is only an instance of an infinite class of inconsistent abstraction principles. Now, if you think about abstraction principles in the abstract, or in this Frege context, what they do is to compress the concepts into the domain of objects according to an equivalence relation on concepts. When one looks at the situation set theoretically, this corresponds to the idea of mapping the power set of a set X into the set X itself, according to an equivalence relation defined among the elements of the power set. In the case of BL5, this relation is the extensional identity of the sets. In the case of Hume's principle, it is the existence of a one-to-one mapping between the sets. So in a Frege setting, an abstraction operator is an operator on concept delta, such that delta x equals delta y if and only if x ey, where E is some equivalence relation on concepts. Now, what would it mean to say that delta must satisfy a part-whole constraint? Okay, this is how we connect this material to Zermelo's theorem. Well, we say that an abstraction operator satisfies part-whole if the following condition holds. For every concepts x and y, if x is strictly included in y, then delta must keep track of that strict inclusion by assigning different values to x and y. So delta x is different from delta y. And this inclusion, strict inclusion, can of course be defined in purely logical terms. And now the question is, can we have, right, so let's call this formula PW for part-whole. But now part-whole does not have a standard model in a Frege setting, i.e., what is a Frege setting? Well, it's a model of the form given by a set X, the full power set of X, and a function f, which sends the full power set of X into X. Why is that? Well, simply because Zermelo's theorem shows that for any X and for any f, if f sends the full power set of X into X, then there must be sets A and B in X such that A is strictly included in B, but delta A equals delta B. So no abstraction operator in a Frege setting can track part-whole. Now, Frege systems, though, are second-order systems. And unsatisfiability, so the lack of a model, does not automatically lead to a deductive refutation of the possibility, right, that there is such a function. So on account of Gödel's incompleteness theorems, in second order logic, the lack of models is not tantamount to having a formally contradictory theory. Or, put it in other way, just because you lack models, it doesn't mean you can refute the statement in the theory. However, in Mancosu and Siskind 2019, it is shown that second order logic can deductively refute the existence of any such operator. In this context, one works in the signature of second order logic with the additional function symbol delta, whose arguments are monadic predicates, i.e. concepts in the Frege jargon, and whose values are objects. Now, the technical details are complex, as one needs to show that in second order logic, one has the resources to bypass the appeal to transfinite induction that is used in the standard proof for Zermelo's theorem. But the formal result can be stated as follows. Let the turnstile denote provability in second order logic with the usual natural deduction rules for quantifiers and connectives, plus substitution rules for first and second order terms, including those that have delta in it. Well, first of all, under extensionality, BL5 becomes for all x for all y, delta x equals delta y if and only if x equals y. We know, of course, and this is Russell's paradox, that in second order logic, plus the additional symbol for the abstraction function, we can refute BL5, okay? Now, again, we have the sentence, part whole, which states that the delta function respects part whole. Of course, part whole is not literally speaking an abstraction principle, though there are abstraction principles which deductively implies the statement part whole. For example, BL5, indeed note that the extension operator characterized by BL5 trivially implies the part whole principle, because if A is strictly included in B, then A and B are extensionally different, and thus delta A is different from delta B. Okay, so there are abstraction principles which imply part whole for that very abstraction operator. So the following theorem gives a new proof of the inconsistency of BL5 and the first proof of the inconsistency of any other abstraction principle that satisfies part whole. Theorem 2.2 in second order logic, plus just one symbol for the extra function, we can refute part whole. The details of the proof are not needed, at least to understand the main consequence of this result. The formal inconsistency, i.e. the deductive refutability of basic law 5, can be seen in the context of a wider family of formally inconsistent abstraction principles, i.e. abstraction principles whose main operator deductively implies part whole. And thus the inconsistency of BL5 is not an isolated fact. Of course, it would be terribly disappointing if it turned out that the only abstraction operator implying part whole is BL5. But this is not so, and in Mancosu and Siskind 2019, we show that there are infinitely many abstraction operators that deductively imply part whole. And by theorem 2.2, they're all inconsistent. Now, one can ask at this point whether all inconsistent abstraction principles satisfy part whole, right? What we have shown is that if an abstraction principle satisfies part whole, then it is inconsistent. But it would be wonderful if it turned out that satisfying part whole is the essential characteristic of inconsistent abstraction principles. But this is not so, because it turns out that there are inconsistent abstraction principles that do not satisfy part whole. And we covered this in our paper. And now this original article contains many more applications and results, but in the spirit of the presentation, I just want to emphasize what I consider to be the most important results of applying Zermelo's theorem in this particular area. And so I'm going to move now quickly to second order logic. So one of the most acclaimed classical results of set theory is Zermelo's proof of the equivalence between the axiom of choice and the statement that every set can be well ordered. Now, since Zermelo, implications and equivalences among various choice principles in set theory have been extensively mapped out. Given second-order logic's expressive resources, it is natural to ask whether second-order logic is strong enough to capture these results. Well, if we try to capture Zermelo's theorem, and here by Zermelo's theorem, I mean the equivalence of the axiom of choice and the well-ordering principle, right? Not the theorem on part all with which I have introduced this talk, we run into expressivity issues. While the property of well-ordering can be straightforwardly expressed in second-order logic, the existence of a covering function, to use the term used by Zermelo, as postulated in the axiom of choice, cannot be expressed in second-order logic. A covering function for a set X is a function that for every subset Y of X, every non-empty subset Y of X, selects an element Y in Y and ends in X. Well, think about it. We are dealing with a map from the power set of X into X. Thus, Zermelo's theorem, i.e. this time the one on part all, might turn out to be relevant. Now, a proof of Zermelo's equivalence theorem can be given in a third order logic, where we have the ability to quantify over what are sometimes called type 2-1 functions, i.e. functions that take elements of the power set of the domain into the domain itself. In third order logic, it is thus not difficult to prove the following. For every set X, there is a covering function for X if and only if X can be well ordered. But what if you don't have the resources of third order logic? Well, then the situation is more complicated. And what we do with Siskind and Shapiro in 2023 is to consider an extension that in second order logic that is similar to the one that the neologicists perform in second order logic. In other words, recall that in the context of neologicism, one works in second order logic extended with a delta, with a 2-1 function constant delta. The function symbol in question is implicitly defined through the abstraction principle. As mentioned, the main result is that any abstraction principle that defines a function satisfying part all is refutable in second order logic. So we take this technique developed in 2019 and we prove new results on choice functions in second order logic. Notice that, like abstraction operators, choice functions assign monadic predicates to objects. For instance, Zermelo's covering function starts with a set M, whose well ordering is sought, and assigns to every non-empty subset Z in M a distinguished element Z in Z. In other words, for each non-empty set M, if you let PM star stand for all the non-empty subsets of M, one postulates the existence of a gamma from PM star into M, such that for every Z in PM star, we have that the representative of Z is in Z. Okay, so now to give you the key results in this application to second order logic. Let W of P for well-ordering principle be the typical statement in second order logic that every concept of the domain admits a well-ordering. In this context, we introduce the following axiom, which expresses that delta is a choice function on non-empty sets. It says that for every concept, if that concept is not empty, then the delta of that concept fall under the concept. Okay, so that we have a representative that falls under X, and that's given by the delta function. So we get, with a small modification of the results from Siskind and Mancosu, two main results. The first is that second order logic extended simply by the function delta plus the axiom choice proves the well-ordering principle. So in other words, if you go above second order logic by adding a constant for to one function which satisfies the choice principle, you get well-ordering. And then theorem 3.2 says that second order logic with the extra symbol plus choice is a conservative extension of second order logic plus the well-ordering principle. So what's the importance of these results? The combined effect of these two results is that we go beyond second order logic only in a limited way, i.e., the same way in which abstractionist neologicist theories, such as second order logic plus HP, Hume's principle, go beyond second order logic. And we obtain an implication from choice to well-ordering, which is unavailable in pure second order logic. It's unavailable because of expressiveness, lack of expressiveness. But one way to put the result is this: a single choice function on the power set of the universe gives us a well-ordering for all the possible concepts. So it's kind of comparable to a kind of a global choice statement. As noted above, the full Zermelian equivalence cannot be regained unless we go to third order logic. But we have the next best thing. Choice does not allow us to prove anything in the old language that WOP, the well-ordering principle, could not already prove. So what this means really is that for any of all the second order versions, pure second order version of the axiom of choice that you can get, one of them is the well-ordering principle. The well-ordering principle is the strongest one. In other words, if you prove something by adding choice, as we did, and something you're proving is in the old language, then well-ordering was enough to prove it. So in this sense, it is the strongest principle. Okay, so that's the application to second order logic. And now I'm gonna move to probability theory for the last 20 minutes. So the standard Kolmogorovian approach to probability theory on infinite sample spaces is neither regular nor total. Please indulge me in this little memory. When I was in Moscow as a visitor of the Steklov Institute in 1990, I was taken to what was the office of Kolmogorov at the State University, and I was allowed to sit in his armchair, which I thought was quite a moving experience. So in Kolmogorov probability theory, a probability space is given by a triple omega B mu, where omega is a set called the sample space, B is a sigma algebra of subsets of omega, and mu is a probability measure assigning a real number in the interval to the interval 0, 1, to every set in B. There is actually a mistake there. It's just assigning a real number in the interval 0, 1 to every set in B. Now, what is regularity? Well, regularity, expressed set theoretically, is the request that only logical contradictions, i.e. the empty set, get assigned probability 0. It is often understood as a bridge principle between modality and probability, stating that no possible event can receive a probability 0 of occurring. Totality, on the other hand, requires that every subset of the sample space omega to be measurable, i.e. to have a probability value. Now, from the point of view of the classical definition of probability, and I mean by classical definition, the one given in Laplace in terms of the ratio between the favorable cases and the full set of cases, it seems almost a triviality that an event with probability 0 cannot occur. This intuition is reflected in what is called regularity. If P is possible, is a possible event, then its probability should be greater than 0. It is indeed difficult to find, before the emergence of measure theory around the beginning of the 20th century, claims to the effect that an event with probability 0 might still be possible. Now, things changed dramatically with the application of measure theory to probability theory at the turn of the 20th century, foreshadowed by Poincaré, who simply asserted that the probability of the rationals in the interval 0, 1 is 0, and by work on continued fractions related to astronomy, the idea that there are non-empty, even uncountable sets of probability 0 enters the probabilistic arena with Borel's development of the notion of Borel measure and the application of Lebesgue measure to probability theory. Now, Borel distinguished between discrete and continuous probabilities. Continuous probabilities could be either denumerable or non-denumerable. This was a theory that Borel was trying to develop, even though nowadays, we just don't have truly a theory of denumerable probabilities. But Borel was very much into this project. For me, what is important is something else. So in 1909, Borel pointed out the contrast between the discrete case and the denumerable continuous probability case when it affects probability 0. And he says, there is a true discontinuity between an infinitely small probability, that is a variable probability that tends towards 0, and a probability that is equal to 0. Indeed, no matter how small the probability of the favorable case is, this is nonetheless possible, whereas it is impossible if the probability is 0. Such are, anyway, the classical results of discrete probability theory. But one knows that things are otherwise in the theory of continuous probabilities. The probability that a number chosen at random is rational is 0. This does not mean that there are no rational numbers. Things will be the same in the case of the denumerable probabilities. Probability 0 should not be considered as the equivalent of impossibility. From that point on, the distinction between probability 0 and impossibility becomes an accepted fact of continuous probabilities. For instance, if you take a look at Hausdorff's classic book on set theory, it says it is also perfectly clear that from this, by a large arbitrary definition, probability 0 is not the expression of impossibility, and probability 1 not that of certainty. For 0 is a probability that a point belongs to a set of 0 measure, which might still be of the cardinality of the continuum. Okay, so let's go back to the formal setup in Kolmogorov approach. So a measure mu in a probability space omega b mu satisfy Kolmogorov's axioms, and this is all standard, if mu of the probability of the sample space is 1, mu of b for any b in the class of subsets is greater than or equal to 0. This is the class of measurable subsets. And then we have countable additivity, which I'm not going to read, because if you know it, you know it. If you don't, you won't learn it by my reading it very quickly. Now, moreover, here is the two additional notions we are concerned with. Mu is regular if mu of A equals 0 implies that A has got to be the empty set for any A in the class of measurable sets you have picked. And mu is total if B happens to be the full power set of the sample space. It is well known that, and this is just one example among many, if we let omega equal 0, 1, we witness a failure of both regularity and totality for many standard Kolmogorovian probability functions. Indeed, suppose mu is a uniform probability function defined on all singletons in 0, 1, i.e. mu of singleton x is defined for any x in 0, 1, and mu of x equals mu of y for any element in 0, y. Then a standard argument that uses countable additivity establishes that mu of the singleton x must be 0 for any element of 0, 1. So this is one of the unpalatable consequences of, or at least one of the unpalatable consequences of this fact is that we have to accept that in a Kolmogorovian setup, whenever we throw a perfectly pointed dart at the interval 0, 1, and we assume uniformity, every single point x in 0, 1 has probability 0 to be hit. Even though, right, one of them will be hit, because there is certainly a possibility that one of them will be hit. So that failure of regularity then is something that, at least intuitively, it's problematic. You just feel that if something is possible, right, if there is a possibility that a single element in 0, 1 gets hit, well, then it shouldn't get probability 0. But under uniformity, that's not what happens in the Kolmogorovian setup. Now, the failure of totality in the Kolmogorovian context often follows from the axiom of choice. For example, Vitali's theorem establishes that there are subsets of the interval 0, 1 that are not Lebesgue measurable. When one does not require the probability measure to be translation invariant, i.e. to give the same value to intervals that are congruent, then the existence of total probability measures on the interval 0, 1 becomes either trivial or independent of ZFC. I'm not going to get into the details of this. Okay, so the failure of regularity and totality in the Kolmogorovian case raises the issue of whether there exist theorems relating regularity and totality that can be stated in more general terms and that apply beyond the context of Kolmogorovian probability. For instance, the failure of totality for the Lebesgue measure uses countable additivity. But what if we weaken our probability function to finitely additive functions? Just to give an example, Banach in 1923 constructed a total, finitely additive, and translation invariant probability measure on 0, 1. But that measure, of course, is not regular. In our account, regularity will fail only when a possible event is assigned probability 0. Now, I'm saying this because there are some accounts given by philosophers of probability that include in the definition of regularity the property of totality. We keep totality and regularity separate because that provides better information about what is going on. Now, philosophers of probability have devoted quite a bit of attention to regularity. Regularity was discussed in several publications of the second half of the 20th century. And one of the reasons why there has been such an interest in regularity is that, for instance, when you're doing formal epistemology and you're looking at functions that that tell you how to update your credences upon receiving new information, those functions get in trouble if the probability of the event which you come to learn was in fact 0 to begin with, even though it was a possible event. because then you end up in your formulas to have to divide by 0 and to do similar things. Same thing for conditional probability. So in other words, there is a sense in which in formal epistemology in particular, it is appealing to be able to say that a possible event has a non-zero probability. Now, the discussion has recently been revitalized by the emergence of powerful infinitesimalist approaches to probability theory, which seems to open new possibilities for a defense of regularity by using infinitesimals in the range of the probability function. So we start going beyond the Kolmogorovian approach, because in Kolmogorov, the range of any probability function is the interval 0, 1. Now the suggestion is that, well, perhaps we should actually work with a non-standard interval 0, 1, where you also have infinitesimals. But some philosophers have found this attempt to save regularity wanting. In particular, Williamson in 2007, Isvara in 2014, and Hayek in 2011 have claimed that the use of infinitesimals is not a satisfactory way of implementing regularity as a constraint on rational credences. For instance, Williamson in 2007 provides a thought experiment with a countably infinite sequence of coin tosses and claims that even with infinitesimals at our disposal, the probability of such a sequence is 0. And yet, such a sequence is possible. Meanwhile, Isvara and Hayek argue that some of the issues for orthodox Bayesianism, which is the standard setup that uses conditional probability in formal epistemology, created by the failure of regularity, are best addressed by a revision of orthodox Bayesianism altogether. If you're not inside this literature, the main thought here is that the standard Bayesian approach starts with the notion of conditional probability and then defines absolute probability in terms, starts with the notion of absolute probability and then defines conditional probability by means of a formula. The suggestion made here by Isvara and in particular by Hayek is we should start with conditional probability as primitive. And in fact, Popper had given an axiomatization by means of Popper functions exactly of this type of approach in probability theory. And they claim that this revision of the orthodox probability setup is sufficient to take care of the kind of problems that, the lack of regularity will introduce, but without the need to appeal to infinitesimals. Regarding the introduction of infinitesimals as a solution to the regularity problem in standard probability theory, now why is the introduction of infinitesimals a solution to the regularity problem? Well, because you can think that when you have singletons in the interval 0, 1, for instance, you're giving them, given that they are possible, not value 0 of occurring, so not probability 0, but rather an infinitesimal. But an infinitesimal, by definition, is different from 0 and less than any finite quantity. So this is the idea of how to get around and how to preserve regularity if you have a non-standard range for your probability function. And the question now becomes, well, if you enlarge the range, are you safe? And this is what starts, according to Hayek, a kind of arms race. It says, we scotched regularity for real-valued probability functions by canvassing sufficiently large domains, making them uncountable. The friends of regularity fought back, enriching their range, making them hyper-real valued. In other words, this is the move of introducing infinitesimals. I counter with a still larger domain. In other words, I'm going to find another non-regular function by using a larger domain. So making this domain hyperreal valued. Now, perhaps regularity can be preserved over that domain by enriching the range again, as it might be, making it hyperreal valued. I counter again with a yet larger domain. Some of its values are hyperreal valued, and so it goes. Some latter-day Bernstein and Wattenberg would need to keep coming up with constructions that would uphold regularity given however big omega gets, presumably with ever richer fields of numbers to provide the values of the probability function. Okay, let me just keep this. So in keeping with the dialectic outline so far, the formal results discussed in the literature on the topic can be roughly divided into two categories. On the one hand, we have existent theorems. Establish that, excuse me, these speakers have so in keeping with the dialectic outlined so far, the formal results discussed in the literature on the topic can be roughly divided into two categories. On the one hand, we have existence theorems, which establish that under certain conditions on the sample space omega and the range of probabilities v, regular probability functions from p to p omega to v can be constructed. So these are existence theorems. On the other hand, we have impossibility theorems identifying conditions on omega and v under which there can be no regular probability measure from p of omega to v. For instance, here is one example of an existence theorem. Let omega be any infinite sample space. Well, then there is a hyperreal field R star of at most cardinality 2 to the cardinality of omega, and a regular probability measure from the full power set of omega into R star. Okay? In other words, given any sample space omega of cardinality kappa, one can always obtain a total and regular probability measure on P of omega by finding an appropriate hyperreal field of cardinality 2 to the k. So all you need is to find a range which is big enough. By contrast, the best impossibility results existing in the literature, well, before our work, because we improved on it, can be found in Mras 2013. Unlike Hofweber, Mras focuses on the size of the sample space. And Mras in 2013 shows that whenever omega is strictly larger in cardinality than the range of a probability measure mu, then mu cannot be regular. Now, all of Mras's results in Mras 2013 require omega to be bigger in cardinality than the range of the probability function. We have no objection to the formal results, and one can see how they relate to the arms race contemplated by Hayek. However, the failure of totality and regularity in many ordinary cases requires weaker cardinality assumptions than the ones required by Mras's theorem. Our aim, thus, is to improve on the cardinality hypothesis needed for the compatibility or lack thereof of totality and regularity. So our main contribution to the existing literature is an improvement of Mras's impossibility theorem. Using a notion of generalized probability measure inspired by Mras's setting, we established the following. Don't worry about this notion of generalized probability range. Just think of it as a range that works for, probability theory. For any generalized probability range and any set omega such that the cardinality of omega is greater than or equal to the cardinality of the range, then there is no total, regular,
V probability measure for omega. Now, this theorem is a clear strengthening of Mras's result, since it establishes that the assumption that the cardinality of omega be strictly greater than the cardinality of the range can be weakened to greater than or equal to. We also combine our novel impossibility theorem with existence theorems, such as the one in Hofweber 2014 and Bench and others in 2018, to address the following question. Given a sample space omega and a cardinality kappa, is there a generalized probability range V of size kappa and a regular generalized probability measure defined on P of omega? And we show that under the assumption of the generalized continuum hypothesis, the conjunction of the non-existent theorems and our impossibility result yields a complete answer to the question we posed above. So here is the theorem. Let kappa be a cardinal and omega a set. Then there is a hyperreal field R of size kappa and a total and regular finitely additive probability measure mu from the full power set of omega into R, if and only if the cardinality of omega is strictly less than kappa. Now, the assumption of the generalized continuum hypothesis is only given here because it makes the statement of this theorem quite compact and nice. There is, of course, also a theorem to be stated without the generalized continuum hypothesis. It's just that it doesn't look so nice because then you have to take into consideration the possibility that that the cardinality of the continuum is not in fact Aleph 1. Okay, so but this is the main result, which gives a full characterization under what conditions you're gonna be able to get a total and regular finitely additive probability measure. Okay, now so far I haven't told you anything about part hole, and part hole, if you recall, was the main subject of the talk. So very quickly now, because time is running out, I want to tell you how the issue of regularity and probability is related with Zermelo's theorem on part hole. Well, as is standard in the literature on generalizations of the Kolmogorov setting, we start with the notion of a finitely additive measure. So probability measures are simply a special case of the following notion. A finitely additive measure is a triple omega A mu, where omega is a non-empty set, A is an algebra of sets over omega closed under finite unions and complements, and mu is an additive function, i.e. the mu of the union of two sets is the sum of the measures of the individual sets whenever A and B are disjoint. And in particular, mu of the empty set is 0. Okay, well, mu of omega A mu is said to be a probability measure when mu takes values in the unit interval, so that the range of mu is included in 0, 1, and mu of omega is 1. Okay, now recall a result that is well known in the literature, but is worth proving expressly. I won't prove it, but I will state it. A finitely additive measure omega A mu satisfies part hole if for any A and B in A, such that A is strictly included in B, the measure of A is strictly less than the measure of B. And the lemma now is that suppose you have a probability measure from the power set of omega into 0, 1. Then, in fact, it turns out that regularity is equivalent to satisfying part hole. Okay, so this is the key connection to the work that we have been doing on part hole, that regularity for a finitely additive measure on the full power set of the sample space is just part hole. This is the proof, but I'm not going to read it because I don't have time, but it's very simple. And now let me remind you of what our original result from Zermelo was. Given a set X and an arbitrary function f from the power set of X into X, there are sets A and B in the power set of X, such that A is strictly included in B, and f of A equals f of B. And now our interest, right, is in applying this to probability contexts where, you know, the set from which you start is some sample space omega, and then you're giving probability values from the power set into the range. So a first application of this, very limited, but just to give you the sense, is suppose your X is indeed the interval 0, 1. Well, then you let mu from, assume that mu from the power set of 0, 1 into the standard range 0, 1 is a finitely additive measure. Well, then mu cannot be regular. Well, this is simple because mu, by sending the full power set of 0, 1 into 0, 1, is regular if and only if it satisfies part whole. But being a function from the power set of 0, 1 into 0, 1, mu must violate part whole by Zermelo's result. And so it cannot be regular. Now, this is a very special case because omega happens to be identical to the range of the probability function. So if we weren't able to generalize, this would be of very limited interest to probability theory. But fortunately, we were able to generalize. And so we can overcome the restrictions of having the sample space equal to the range. And here is how it goes. This is just the first generalization. There is much more in the paper, but I only, as I said, want to give you a sense of these results. So suppose you have X as a subset of 0, 1. And now suppose there is a surjection F, where F is going to be just a function from the sample space omega into X. You know, the fact that you have a surjection basically tells you that the cardinality of omega is at least as big as that of X. Well, then you can show that there is no regular finitely additive probability function mu from the full power set of omega into X. And so as an immediate corollary, we obtain the following. Let omega be a set such that the cardinality of omega is 2 to the Aleph naught, then no finitely additive probability measure mu from the full power set of omega into 0, 1 is regular. And the proof is just this diagram. So the function f, right, is the surjection from omega, which is the sample space, into the range. And now you see we want to bring things back to the setup for Zermelo's theorem. And the way you do that is to consider f star, which is the inverse image lift between p of omega, p of x and p of omega. Then you do the composition of that with the function mu that is supposed to be the probability measure from p of omega into x. And that composition, as you see, is sending you from the power set of x into x. Now we are back in the Zermelo setup, so that we know that that function, mu composed with f star, must defeat part whole. But if it defeats part whole, then by the equivalence between part whole and regularity, it also defeats regularity. So that's the connection to the, and this is the last slide. So the fact that in the classical Kolmogorovian context, the range is 0, 1 leads to the issue of what happens if one chooses a range that is non-Archimedean. And in the paper with Massa, we move to this greater level of generality by investigating applications of Zermelo's theorem in a more general setting in which the range of a probability measure mu is not assumed to be contained in the unit interval 0, 1. And this has two goals. One, getting closer to Hayek's arms race, and two, understanding better the relationship between totality, regularity, and cardinality outside of the Archimedean context. But here I will stop. Thank you very much.
Professor Mancosu, thanks a lot for your talk. It was really, really great. So we're going to the question sections. So, dear participants, if you have some question, you can just raise your hand in Zoom or write your question in the chat. Also, we have some questions from the Telegram chat. So, okay, first of all, I also have a question. So, the axiom for the axiom choice, to out a genuine choice function in the context of extended second order logic. So it is necessary to either assume properties are extensional or that coextensive properties always map to the same abstract object. For example, for all x and y, if x equal to y, then delta function x is equal to the delta function y. And how does this requirement, the premise of extensionality regarding properties, relate to the broader philosophical goals of abstraction, neologicism, upon which this methodology relies, and does it call into question the very possibility of operating with intentionally distinct or yet extensionally equivalent predicate?
Yeah, thank you. Actually, so we pay special attention in the paper to this issue about where extensionality is needed and where not, and we provide a number of scenarios which I cannot summarize here concerning what happens under different scenarios. But in fact, extensionality is not it's not really needed, except when in the case of the choice context, you can also get by in situations where you don't have extensionality. The assumption of extensionality is just convenient, though, because it's more natural in certain ways. Yeah.
Yes, thank you. And the next question. So, how it formulates? It's kind of philosophical question. So, what ultimately is the role of second order logic, as you see it in the neologist project, and if at this so suggests proving fundamental theorems like Zermelo's requires an extension of second order logic by introducing the abstractor, which essentially introduce a new kind of entity created from properties, as I understand it. Does this undermine the thesis that arithmetic or set theory can be reduced to pure logic, albeit an extended one?
Yeah, thanks for this question. I mean, that raises a lot of interesting issues. Most of the problem here is that, of course, there is one basic starting problem, which is to say, consider pure second order logic. Does that ought to count as logic, or is that actually some sort of hidden mathematics? You know, very famously, Quine was against second order logic as logic because he thought it was just set theory in disguise, right? He used to speak of second order logic as, you know, kind of a sheep in a wolf in sheep's clothing. But let's put for a second this issue, which, as I say, has been much discussed in the literature, of whether second order logic is in fact logic as opposed to a mathematical system. Well, even with that on board, the question becomes, well, what to say about Hume's principle, which is the other addition that a neologicist makes to the system in order to be able to derive the second order Peano axioms. And there, the neologicist does not say that that Hume's principle is a logical principle. Rather, they say that it's a form of definition, and so it can be considered to be in the category of the analytic, using a Fregean and Kantian notion, which has a long history to our days, and or something, they say, akin to analytic. So their gambit is the following. Pure second order logic is kosher because they take it to be logic. Then the addition of Hume's principle, it's a sort of definitional addition that tells you what the meaning of the number of operator is. And although they do not say that the resulting system is pure logic, what they do say is that from the epistemological point of view, taking on board Hume's principle doesn't take you out of the realm of the analytic, which should have the epistemological advantage that you know, you can recognize its truth, you know, virtually just in virtue of the meaning of the symbols that are being used, of the concepts that are being used in that definition, and so on. Of course, that's exactly where the discussion for 40 years has been focused on, whether it makes any sense to claim that this principle, Hume's principle, is in fact analytic in this sense. For instance, Boulos used to object that, you know, in reality, Hume's principle is an axiom of infinity, because as soon as you know, add it to second order logic, you get infinitely many elements out of it. And according to a certain conception of the analytic, you know, you couldn't have an analytic statement being so ontologically, as it were, productive, right? If something is analytic, you shouldn't have, you know, it would be surprising if it gives you such a substantial ontological commitment and so on. And so the discussion has been going back and forth. So my personal point of view is that I tend to side with Boulos on this. So I find the Neologicist program interesting, and I find the problems that have come up from discussing its viability to be very interesting, but I don't really believe that the goal of showing the analyticity of you know, the theory of second order logic plus Hume's principle has been achieved. But one final thing, just to identify the point of separation between Frege and the neologicist. The neologicist says it doesn't really matter if you can reduce second order arithmetic to logic. That's what Frege wanted to do it, but really he wanted to reduce it to logic only to show that arithmetic was analytic. And so the reduction to logic was instrumental for proving the analyticity of second order arithmetic, whereas we don't pass through the reduction to logic and simply go to a claim of the analyticity of the system, because we claim that Hume's principle is analytic, and then of course we claim that any transition in second order logic by means of second order logic preserves analyticity. So that's the big distinction between neologicism and the Frege approach.
Yes, thanks, Alon. And the near question. So, as I know, there are nowadays some people wanted to reborn a Hilbert program. So,
Yes.
do you think that it will help to the global logic, or it's uh, a bad way?
Mm. I'm not sure about the question you asked, actually. So, so the Hilbert program is, it's been in a way in a revised form, alive since even the downfall of the original program on account of Gödel's incompleteness theorems. Because as soon as people got persuaded, it took a couple of years. Originally, both Gödel and Bernays weren't quite sure whether the Gödel incompleteness actually killed the original version of Hilbert's program, because they thought, well, maybe there are finitistic reasonings that escape even Zermelo-Fraenkel set theory or second order arithmetic or something. Well, then eventually they got convinced that all of finitism was included in piano arithmetic, so that in fact Gödel's incompleteness was a blow to the original Hilbert's program. And then starting from there, of course, we move to generalized or extended versions of Hilbert's program, where you take on board constructivist principles that escape the original notion of finitism, but they still might provide you with epistemic advantages. Of course, it's known that the proof by Gensen with epsilon zero induction, or the decision by Gödel in the Dialectica interpretation to use recursive functionals of finite type, are all ways of extending the original finitism. But so this is the setup. But now, can you repeat the part of your question concerning why this, as it were, preservation of Hilbert's program would affect second order logic?
Oh, yes, in kind of way. So, as I know, for example, where the latest Kripke's works were on the Hilbert program, and he believed that it's not just that. So we can uh, go again to this program and re-research it or just reborn. So probably it can be applied to the second order logic too.
Mm. Yeah, I'm not. Yeah, I don't have in mind right now these passages from Kripke, so I think I will refrain from commenting on it, because I don't see a way in. I mean, to me, second order logic as a formal system, so the syntactic part, is not particularly problematic, in the sense that you can show the consistency of second order logic just as you do for first order logic. And after all you need to do is to provide a domain with one element and two subsets. That's really all you need to show that consistency of second order logic. But I'm sure there must have been something different going on in what Kripke was saying, because this is it's too trivial. Right. So the consistency of first order and second order logic are not particularly problematic per se. But maybe there was something else that was being claimed. Maybe it wasn't the syntactic formalization of second order logic, but something that may be related to the semantical consequence relation, which of course would be very different, because we know that's not even arithmetical, right? It's so I'm gonna leave it at that.
Yeah, okay, thanks. So Kazakov Yuri have a question. So Yuri?
Yeah, thank you, Amazon. Thank you a lot, Professor Paolo, for your presentation. My question is always about my understanding. I want to request about your article in 2019. We clearly have a significant distinction between finite and infinite concepts in all this framework. So can the principle of part wall be extended on finite concepts? And do we have any reason to believe that nothing will break in this case? Well, that's...
Yeah, sure. Thank you for the question. Yeah, I don't see any abstraction to the application of part whole, because part whole, as we're treating it, it's simply subset inclusion and proper subset inclusion. And that notion applies, within finite and infinite sets just as well. So, for instance, there is no problem in saying that the even numbers, if we were able to have the natural numbers in our domain, are strictly included in the natural numbers. And in the case of Hume's principle, what we end up saying, because if we have Hume's principle, we do generate the natural numbers, so we can apply the concept of number of to infinite sets. In the case of Hume's principle, we would have to say that the number of the even numbers is equal to the number of the natural numbers, because we can prove in the system that there is a one-to-one correspondence between the two. So I see no difference in principle with applying these notions of part whole to finite or infinite sets. But perhaps what is in the background of your question is what actually led me in the first place to all these projects, which is, but what about ways in which you might assign sizes or numbers, if you want, to infinite sets that do not respect Hume's criterion? In other words, suppose you want to play with possibilities of assigning sizes to the even numbers and the natural numbers, according to which the size of the natural numbers is strictly less than the size of the even numbers is strictly less than the size of natural numbers. Okay, I've been writing a lot about this, not in this specific paper, but in my book Abstraction and Infinity, and now in a new book that is coming out in a few months for Oxford University Press called The Wilderness of the Infinite. There things become really interesting, and that's what led me to part whole. So let me explain quite quickly. There is a new theory called the theory of numerosities, which allows us to give non-Cantorian assignments of sizes to sets. And this theory preserves the intuition of part whole, meaning that if you have two sets, one of which is a proper subset of the other, then the numerosity, the size, if you want, of the set which is included in the other set is strictly less than the size of the including set. So to give you an example, if you take the natural numbers and you pluck away one element from them, you take away the number 17, well, the numerosity of the set of natural numbers without 17 is going to be strictly less than the numerosity of the natural numbers. And this is a much finer way of counting infinite sets, which in the finite coincides with the Cantorian approach. So there is no distinction in the finite between numerosity theory, Hume's principle, and Cantor's assignment of cardinalities. But things become very different where you go when you go to infinity. Because, as I said, in numerosity theory, the even numbers and the natural numbers have different numerosities. But according to Hume's principle or to Cantor, they are identical in size, right? They're both Aleph 0. And this is what led me to this stuff about part whole, because the theory of numerosities implements part whole across the board. In other words, it finds a way to number sets so that the numerosity function tracks the subset inclusion, proper subset inclusion. And now you might, at this point, given my talk, ask, well, isn't that a contradiction with what you just told us about the fact that Zermelo's theorem on part whole tells us that any kind of function from the full power set into the set is going to defeat the tracking of part whole? Well, the reason why numerosity theory can achieve what it does, and you can't do such things in the Frege context, is that in numerosity theory, you're not sending back the value of the function into the original objects. You're working really in a kind of non-standard model type of construction where you give values to your concepts or subsets by enlarging your domain. But this possibility is excluded in the Frege setup, because in the Frege setup, you start from a model, a domain of individuals that is given once and for all. And what you're mapping is the full power set into that original set. Whereas in the case of numerosity theory, you start, say, from the natural numbers, but then you construct these new non-standard elements in terms of sequences of natural numbers so that you end up with something bigger than what you had to begin with. Okay, so it was a long answer, but your question was very interesting, so I took the time to address it.
Thank you a lot.
We also have a question or commentary from Saintian Roy. So he said, it would be quite interesting to see a category theoretic generalization of Zermelo's theorem, and I'm not sure there's exists one already.
Yeah, my answer to that is that I'm not aware of one, and I agree. It would be interesting to see, to see a categorical theoretic presentation of such a result. Yeah.
So, the participants, is there any other questions? So then I think There is no questions. So, Professor Mancosu, you want to say anything else?
I just wanted to thank you for being an attentive audience, and it was a great pleasure to get to know you, at least virtually, and possibly in a not too distant future we might even meet personally. Thank you very much.
Professor, thank you. Thank you too. It was really great and pretty nice. So, hope see you again at the same time.
All
Thank
right. Bye
So,
bye.
bye bye. Have a nice day.
Thank you so much. Bye bye.
See you.